Alright, let's go. Number 8. The strength mismatch. In the late 1970s, particle physicists working on grand unified theories were trying to solve a bookkeeping problem. They wanted to write down the mass of the Higgs boson using quantum field theory and find a natural reason it sat where it sat. Kenneth Wilson at Cornell had already shown that quantum corrections should drag any scalar mass up toward the highest energy scale in the theory. When they did the calculation, the correction wasn't small. It was catastrophic. Standard physics has 4 fundamental forces. 3 of them, electromagnetism, the weak nuclear force, the strong nuclear force, sit within a few orders of magnitude of each other. That's what the equations expect. That's what a well-behaved universe looks like. Everything talks to everything else on roughly the same scale. Then you add gravity, and the numbers stop making sense. Gravity is weaker than electromagnetism by a factor of roughly 10 to the 36. In a 1998 paper in Physics Letters B, volume 429, Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali laid the discrepancy out in its starkest form. The gap between the electroweak scale and the Planck scale is roughly 1017, and the mass squared hierarchy that follows is 1034. A cheap refrigerator magnet, the kind you find on cereal boxes, defeats the gravitational pull of the entire Earth's mass on a paperclip. Every proposed solution has failed to close. Supersymmetry predicted partner particles at LHC energies to cancel the corrections. The LHC ran through the entire predicted mass range and found nothing. Arkani Hamed's own extra dimension proposal, that gravity leaks into hidden compact dimensions, has been searched for at colliders and in torsion balance experiments since 2003, with no signal. Technicolor was killed by the Higgs discovery. The anthropic multiverse answer, that we happen to live in the one universe where the numbers permit our existence, is unfalsifiable by construction. Nobody has solved it. Which means the reason your body doesn't collapse into your bones under the pull of the planet you're sitting on, the reason gravity is gentle enough for life to exist at all, has no known cause. It's a number scientists write down and cannot derive. Why is the force that shapes every star and galaxy the feeblest thing in the universe by 36 zeros? Which brings us to a particle that should exist and has never once been detected. Number 7. The Missing Graviton. In 2013, Freeman Dyson at the Institute for Advanced Study was thinking about a question most physicists had quietly ignored for decades, whether the particle everyone assumed carried gravity could ever actually be seen. He wasn't trying to disprove its existence. He was working out the numbers on what a real detector would require. Quantum field theory demands that every fundamental force be carried by a particle. Electromagnetism has the photon. The strong force has the gluon. The weak force has the W and Z bosons. Each was predicted, each was later detected. Gravity, if it obeys the same rules, must have its own mediator, the graviton. It was predicted in the 1930s. It has never been seen. Dyson calculated what it would take to detect one. His answer stopped the conversation. In his paper, Is a Graviton Detectable?, published in the International Journal of Modern Physics A, volume 28, in 2013, Dyson showed that any detector sensitive enough to register a single graviton from an astrophysical source would need to have a mass comparable to the planet Jupiter. It would have to sit in the accretion disk of a neutron star to catch a signal. Any smaller detector, he argued, would be swallowed by its own thermal noise before a graviton ever hit it. LIGO's 2015 detection of gravitational waves is often quoted as evidence for gravitons. It isn't. LIGO measures the classical wave, the coherent movement of trillions upon trillions of graviton quanta at once, if they exist. Proposed single graviton experiments using stimulated acoustic resonators, published by Michael Tobar and collaborators in Nature Communications in 2024, remain theoretical proposals. Cavity-based detection schemes suggested by other groups have never left the drawing board. Every direct experiment ever attempted has produced nothing. The particle that supposedly transmits the force, keeping your feet on the ground, keeping your blood inside your vessels, keeping the sun from flying apart, has never been observed doing so. Not once. It may not exist as a discrete quantum at all. If gravity has no particle, what exactly is transmitting the force pulling you toward the center of the Earth right now? Sometimes the failure is smaller and stranger. 2 spacecraft, a slow drift, 20 years of doubt. Number 6. The Pioneer Anomaly. Starting in the early 1980s, John Anderson and his team at NASA's Jet Propulsion Laboratory were doing what should have been the most boring job in space navigation, tracking the exact position of 2 probes, Pioneer 10 and Pioneer 11, as they coasted out of the solar system. Both had already completed their planetary missions. They were just data points now, sailing into deep space on well-understood trajectories. Newton's laws, with Einstein's relativistic corrections layered on top, predict exactly where a spacecraft should be at any given moment. The sun's gravity slows an outbound probe at a rate you can calculate to 12 decimal places. The equations were built, tested, and trusted for 3 centuries. There was no reason to expect surprises. Anderson found the craft weren't where they were supposed to be. Both of them. By the same amount. In a 1998 paper in Physical Review Letters, Volume 81, Anderson and collaborators reported an anomalous sunward acceleration of 10 meters per second squared. The signal persisted from 1980 through 2002. It wasn't drift. It wasn't measurement noise. Both spacecraft on opposite sides of the solar system appeared to be decelerating faster than gravity accounted for. Every conventional explanation was tested and abandoned in sequence. Solar radiation pressure, wrong sign, wrong magnitude. Interplanetary dust drag, nowhere near strong enough. Fuel leaks, no correlation with the timing. Onboard gas emissions, inconsistent between the 2 craft. For 20 years, serious papers in refereed journals considered whether gravity itself needed modification at low accelerations. In 2012, Slava Turishev and collaborators published a resolution in Physical Review Letters, Volume 108, tracing the anomaly to uneven thermal radiation from the spacecraft's radioisotope power systems. The gravity crisis was over, but it had lasted 2 full decades. For 20 years, the most tested law in physics was seriously suspected of being wrong, because 2 probes drifted a few kilometers off their expected paths. If you can miss something as small as thermal recoil for that long, what else is being missed right now, in front of us, uncorrected? How many other Pioneer anomalies are sitting in current data, signals we've already recorded? Waiting for someone to notice they don't fit? The next problem isn't about missing data. It's about a symmetry the universe refuses to obey. Number 5. The one-way force. In 1957, Hermann Bondi at King's College London was working through the mathematical consequences of Einstein's field equations. He wasn't trying to overturn physics. He was probing what the equations formally allowed, the way a mathematician tests whether a theorem accepts negative inputs. Gravity, in general relativity, is geometry. Bondi wanted to see whether that geometry could bend the other way. Every other force in nature comes in 2 flavors. Electromagnetism attracts and repels. The strong nuclear force binds quarks and, at close range, pushes them apart. Positive and negative charges. Attraction and repulsion. Symmetry is the norm. In physics, when a force only ever pushes in one direction, that's not simplicity. That's a red flag. Every gravitational measurement ever taken shows attraction. Only attraction. No exceptions. Bondi's paper Negative Mass in General Relativity and Reviews of Modern Physics, Volume 29, in 1957, showed the field equations don't forbid negative mass. They simply produce strange runaway pairs, where positive and negative masses accelerate together forever. In 2023, the Alpha collaboration at CERN, in a paper led by E. K. Anderson and published in Nature, Volume 621, dropped antihydrogen atoms in a vertical trap and watched them fall, downward, with the same acceleration as ordinary matter. Antimatter was the last serious candidate for gravitational repulsion. It failed. Every proposed source of gravitational repulsion has collapsed under experiment. Antimatter, ruled out in 2023. Exotic matter with negative energy density, required by traversable wormhole solutions, never observed in nature. The runaway pair paradox of negative mass, first noted by Bondi himself, means any negative mass in the universe would already have accelerated to infinite velocity by now. And we don't see it. Dark energy causes cosmic expansion but doesn't gravitationally repel local objects. It acts uniformly across space. Which means gravity is the only force in nature with one direction. Something about mass, or about space-time itself, forbids repulsion at every scale ever measured. Nobody knows why the universe would build asymmetry into its most universal law. Is gravity's one-way behavior a deep property of reality, or a limit on what we've thought to look for? The asymmetry gets stranger when you look at what's holding galaxies together. Number 4. The missing mass problem, and the theory that says there is no missing mass. In the late 1970s, astronomer Vera Rubin's measurements of galaxy rotation curves had produced a crisis. Stars at the edges of spiral galaxies were orbiting far too fast, as if the galaxies contained several times more mass than the visible stars accounted for. Most physicists concluded dark matter must exist. Mordechai Milgram, working at the Weizmann Institute of Science, took a different approach. He asked whether Newton's law of gravity itself might change at very low accelerations. Under Newtonian gravity, the orbital velocity of a star should drop off as its distance from the galactic center increases, the way outer planets orbit the sun more slowly than inner ones. Every spiral galaxy in the sky violates this prediction. The rotation curves stay flat, out to the edge. Add invisible mass, and the equations balance again. Milgram noticed something no one else had. The discrepancy always kicks in at the same acceleration threshold. In 3 consecutive papers in the Astrophysical Journal, Volume 270 in 1983, Milgram proposed modified Newtonian dynamics, MOND. The threshold he identified, now called Milgram's constant, is roughly 1.2 10 merts 10 meters per second squared. Below that acceleration, gravity begins to strengthen in a specific way. His formula predicted galaxy rotation curves, hundreds of them, across every type of spiral galaxy, with astonishing accuracy, using no invisible mass at all. MOND has been fought for 4 decades. In 2006, Douglas Clow and collaborators published bullet cluster observations showing gravitational lensing offset from visible matter, presented as direct empirical proof of dark matter. And a serious blow to MOND. But MOND still predicts individual galaxies more cleanly than the standard dark matter model, which requires custom halo fits for each system. Jacob Bekenstein's relativistic version, TEVES, published in Physical Review D, Volume 70, in 2004, has struggled with gravitational wave data. No relativistic version of MOND is fully accepted. And no observation has definitively killed it either. Which means 4 decades in, one of 2 possibilities is still open. Either 85% of the universe is made of invisible material that has never been directly detected, or Newton's law is wrong at the accelerations that govern every galaxy in the sky. Both answers are catastrophic for what we thought we knew. What if the reason we can't find dark matter is that we've been searching for the wrong kind of missing thing? Now the scale flips from the galactic to the personal. Number 3, gravity bends time over the height of your kneecap. In 2010, a team led by Chin-Wen Cho at the National Institute of Standards and Technology in Boulder, Colorado, was pushing the sensitivity of aluminum-ion optical clocks to new records. They weren't trying to test relativity, they were trying to build a better clock. But their instruments had become so precise that Einstein's predictions were no longer background theory. They were measurable output. General relativity says a clock closer to a massive object ticks more slowly than a clock further away. This effect had been measured before, with atomic clocks flown on aircraft and satellites at altitude differences of thousands of meters. The prediction was solid. What Cho's team could do was shrink the distance until the effect became personal. They set up 2 aluminum ion clocks and raised one by 33 centimeters. The higher clock ticked faster. The result, published in Science Volume 329, in 2010, under the title Optical Clocks and Relativity, measured a fractional frequency shift consistent with a gravitational time dilation of roughly 4×10^17 per meter of altitude. That's Einstein's prediction, measured over a distance smaller than the width of a laptop. Repeated, reproduced, physical time itself moves at different rates between the top and bottom of your desk. There is no conventional explanation to explain away. The effect is a direct consequence of general relativity. But what relativity does not explain is the mechanism. Why does the presence of mass slow the flow of time? Einstein's equations describe the geometry, they tell you the metric warps in the presence of energy, but no theory tells you why energy warps geometry, or what geometry actually is at its most fundamental level. It is one of the deepest unanswered questions in physics, hiding inside a formula everyone uses. Your head is aging faster than your feet. Right now, every cell above the level of your knees is running through time slightly ahead of every cell below them. The effect is small, nanoseconds per lifetime, but it is real, and it is happening in your body as you listen to this sentence. What is the mechanism by which mass reaches into time itself and slows it down? That personal effect gets worse when you try to write it down mathematically. Number 2, the theory that refuses to be quantized. By the early 1930s, physicists had built quantum electrodynamics, a working quantum theory of light and matter. It was the greatest triumph of theoretical physics. The natural next step seemed obvious: do the same for gravity. Lon Rosenfeld in Belgium published the first attempt in 1930. Every physicist since has assumed it was a matter of time. Nearly a century later, no working version exists. Every other fundamental force fits into the framework of quantum field theory. Feynman diagrams calculate probabilities of interactions. The infinities that show up in the math can be absorbed into a small number of renormalized quantities, masses, and charges. The predictions match experiment to 12 decimal places. Gravity ought to submit to the same procedure. It doesn't. It breaks. In a 1974 paper in Annales de l'Institut Henri Poincaré, Gerard de Hooft and Martinus Veltman showed that pure gravity is renormalizable at one loop. In 1986, Mark Goroff and Augusto Sagnotti published a paper in Nuclear Physics B, volume 266, extending the calculation to 2 loops. At 2 loops, gravity's infinities cannot be absorbed. The theory produces meaningless answers. Every prediction breaks down at energies approaching the Planck scale, roughly 1.22 10 pels 19 giga-electron volts. Every rescue attempt has stalled. String theory replaces point particles with vibrating strings and requires either 10 or 11 dimensions. None of the extra dimensions have been detected. Its landscape contains an estimated 10^500 possible vacuum solutions, with no known principle to select ours. Loop quantum gravity, developed since the 1990s by Abbe Ashtekar, Carlo Rovelli, and Lee Smolin, quantizes spacetime itself into discrete units, but has struggled to recover classical general relativity in its low-energy limit. Steven Weinberg's 1979 asymptotic safety proposal, causal dynamical triangulations, spin foam models, none has produced a testable prediction. Every serious attempt has failed to unify gravity with quantum mechanics. The 2 most successful theories in the history of physics, general relativity, which describes the universe on the largest scales, and quantum mechanics, which describes it on the smallest, are logically incompatible. Both cannot be right in their current forms. One of them is fundamentally wrong. We have no idea which. What are we not seeing about reality that would let these 2 theories agree? The last one goes further than incompatible. It goes to whether gravity is real. Number 1, the theory that says gravity does not exist. In 2010, Erik Verlinde at the University of Amsterdam wasn't trying to overturn Isaac Newton. He was studying holographic entropy, the idea developed in the 1990s from black hole physics that all the information in a volume of space can be encoded on its boundary. Ted Jacobson had already shown in a 1995 paper in Physical Review Letters, volume 75, titled Thermodynamics of Spacetime, that Einstein's field equations could be derived from thermodynamics, treating gravity not as a fundamental law, but as a statistical consequence of something deeper. Verlinde pushed further. Physics has always treated gravity as fundamental. Newton's inverse square law, Einstein's field equations, these are the base layer of reality, the rules from which everything else emerges. Verlinde asked what would happen if gravity was not a base layer at all, but a side effect. The way pressure isn't a fundamental force, it's what emerges from countless molecules colliding. Verlinde asked whether gravity might emerge from the way information is distributed across spacetime. He derived Newton's law of gravitation from an entropy calculation. Verlinde's 2011 paper, On the Origin of Gravity and the Laws of Newton, was published in the Journal of High Energy Physics, issue 04, article 029. In his 2016 follow-up, Emergent Gravity and the Dark Universe, he extended the argument to derive galaxy rotation curves, the same curves usually attributed to dark matter, from entropy alone. In 2017, Margot Brouwer and collaborators, publishing in monthly notices of the Royal Astronomical Society, tested Verlinde's predictions against gravitational lensing data from over 33,000 galaxies. The results were broadly consistent with emergent gravity. Emergent gravity has not been proven, but it has not been ruled out. Predictions in some galaxy clusters have missed observations. The theory currently only handles static, spherically symmetric systems. It has no dynamical formulation. Mainstream physics remains committed to gravity as fundamental and dark matter as real. But the calculations that produced Verlinde's predictions have not been shown to be wrong. Jacobson's original derivation still stands. The possibility remains open. The force holding you to your chair, holding the atmosphere to Earth, holding the moon in its orbit, and the galaxies in their filaments, may not be a law of the universe at all. It may be a shadow cast by something more fundamental, something we have not yet identified, operating at a level we cannot yet see. Gravity, in Verlorne's picture, is not real in the way we think it is. If gravity is only a side effect, what is the deeper machinery of reality actually made of? 8 facts, and every one of them sits at the center of physics, not the edge. This is the pattern. The unsolved problems are not exotic edge cases and obscure theories. They are the most familiar force in your life. Gravity keeps your body attached to a planet, and no one can tell you what it is, why it is so weak, whether it has a particle, why it only pulls, or whether it exists as a fundamental law at all. The universe is not confused. We are. And the thing pulling you toward your chair right now is the thing we understand least. If you want to see more videos like this, click the video on screen now.